All right, so we talked about RSA encryption in class yesterday, and we went through a bit of the mathematics of how this works with respect to number theory and modular operations, and we used the Chinese remainder theorem and Fermat's little theorem and Euclid's algorithm and a few other things to sort of make an argument for why the decryption key actually decrypts the encrypted text. And I wanted to go through an example of actually using RSA to do some encryption, and I didn't want to take class time for that because it can take a while and it's a lot of legwork to do by hand, but it's instructive to see it, I think. So I wanted to go ahead and just run through a simple example by hand for a few reasons. One, to give you another view of the algorithm itself for encrypting and decrypting. And two, to illustrate, that a lot of these things, even though we're working with relatively large numbers, can be done without too much work because we keep reducing modulo some moduli, and that makes the calculations tractable. I also wanted to show you some tricks for doing modular arithmetic with a pocket calculator. If it doesn't happen to have a mod operator, even though we might be working with numbers that are potentially very large. So we're going to use the same secret message that we were trying to encode yesterday, which was happy. And remember to create an encryption key, we need a pair of primes. Okay, so I'm going to start off with some extremely large primes. P is going to be 37, Q is going to be 101. 3-digit prime, how about that? Right. So in practice, these would be several hundred digits, and we'd be using a computer to do this. So I've got pretty small numbers here, but it'll make this doable by hand. All right. So the encryption key is two numbers. The first is the product of the primes, which is just going to be 3737. All right. That's the first part of the key. The second part of the key, we need to find an E such that the GCD of E and P minus 1 times Q minus 1 is equal to 1. In other words, we need an integer that's relatively prime to P minus 1 times Q minus 1. And I'm going to flip to another piece of paper to do that calculation. So how do we find something relatively prime? This is not too hard to do. So we're looking for something relatively prime to 36 times 100. All right. Well, 36, this is 6 times 6, which is 2 times 3 times 2 times 3. So this is 2 squared times 3 squared. And 100 is, 4 times 25, which is 2 squared times 5 squared. So the common factors between 36 and 100 are basically 2 squared, right? And anything else will not be a common factor between those. So, I could pick, 7, I could take powers of 3, and so on and so forth. But I'm also really safe picking a prime number that's not a factor of either of these numbers. So I'm just going to pick 23, okay? Probably not a terribly great choice, but this is a sample example. All right, so 23 is going to be my number relatively prime to P minus 1, Q minus 1. So my encryption key is the following ordered pair: 3737, comma 23. That's the public key that I put out there for the world, and I say, hey, anytime you want to send me a message, encode it using this pair of integers. All right. Now, as the person who came up with this key, I need to also figure out what the private key is. All right, so here's the secret work that I don't tell the public about. So to find the decryption key, I need to find an integer d such that d times e is congruent to 1 mod 3600. Well, my E was 23, so I'm trying to find an E so that 23E is congruent to 1 mod 3600. Can I do this? Yeah, I can. Why? Because 23 and 3600 are relatively prime, right? That's how my criteria for E guarantees that. So 23 and 3600 are relatively prime, which means the greatest common divisor is 1. Well, remember this fact that GCD of A comma B equals F. Then there exists xy, which are integers, such that ax plus by equals f. In other words, if the greatest common divisor of two numbers is f, you can find a linear combination of those in integers that adds up to f. So in this case, we're guaranteed that there's integers, so that 23 times something plus 3600 times something equals 1. Okay, that's a consequence of the GCD being 1. But if we can find our integers that make this equation true, then 23 times this will be a multiple of 3600 plus 1. Right? It'll be 1 more than a multiple of 3600. So how do we find the numbers that satisfy this equation? Well, let's go to another page, and this is going to be running Euclid's algorithm kind of in reverse, or possibly sideways, if you like. So let's use Euclid's algorithm and find the GCD of 3623. So how does this work? 3600 equals something times 23 plus something. All right, calculator time. 3600 divided by 23. So it goes in 156 times. And if I want to know the remainder, I can do the following. I can do 3600 minus 156 times 23, and I'll get a remainder of 12. But there's an easier way to do remainders. Once I've done 3600 divided by 23, and I see it's 156 point something, if I subtract that integer part and then multiply the decimal I've got by 23, there's my remainder 12. And we're going to do this a lot when we do our modular exponentiation. It's going to be quicker than going back and subtracting, n times some number. So we'll come back to that. But anyway, this equation is true. Okay, so 3600 is 156 times 23 plus 12. If I continued to find the GCD, 23 equals 1 times 12 plus 11. 12 equals 1 times 11 plus 1. 11 equals 11 times 1 plus 0. Once we get down to a 0, there's our GCD. Now, in general, there's a way to reverse all of this to come up with this desired linear combination of your two numbers that add up to your GCD. But I got to cheat a little bit here, because really, once we get here, we're almost done, because 12 is really close to 11. So I'm just going to make the following observation and admit that this is a bit of a shortcut. So I'm going to say 3600 equals 156 times 23 plus 12. I'm going to multiply both sides by 2 and say 2 times 3600 equals 312 times 23 plus 24, which is equal to 313 times 23 plus 1. All right, so 2 times 3600 is 313 times 23 plus 1. I'm going to negate everything. I'm going to say negative 2 times 3600 equals negative 313 times 23 minus 1. And now I'm going to flip things around and say 313, well, I'll leave that over there. Negative 2 times 3600 plus 1 equals minus 313 times 23. Okay, what does that mean? It means this is one more than a multiple of that. right? Now what am I trying to do here? I'm trying to find a D such that D times E is congruent to 1 mod 3600. In other words, I'm trying to find something that when I multiply by 23 is 1 more than a multiple of that. Well, here we go. If I take this and multiply by 23, that's 1 more than a multiple of that. So a valid value for D could be minus 313. But we don't want negatives. Negatives are suspicious and so on. But D could be any number congruent to minus 313 mod 3600. Well, let's just change this into a non-negative. So 3600 minus 313 would be 3,287. And that's a nice number. All right, let's double check. Let's take 3,287, multiply by 23. That's the product, subtract 1, and we end up with 75,600. Divide that by 3,600. It divides exactly 21 times. So this number D times our original E is 1 more than a multiple of 3,600. This is going to be our secret decryption key. All right, so let's write that down somewhere. So our secret decryption key is going to be 3,287. All right, so that's how we encrypt, that's how we decrypt. So let's go back to the original goal, which was somebody wanted to send us a secret message. So they're going to send us the message happy. Okay, so the next step of RSA was figuring out your block size. And I'm going to use the following coding. I'm going to use a space is 0, 0, A is 0, 1, B is 0, 2, Z is 2, 6. So the largest message I could encode, largest integer value, would be a bunch of Z's, which would look like 26, 26, 26, and so on. Okay? The encryption algorithm says that we should find how many of these we can put side by side and still have it be less than or equal to n. And remember, our n is 3737. Well, pretty clearly that's 2 of these, the letter Z, followed by the letter Z. If we tried to code this message, ZZ, that would translate to an integer 2626. That's smaller than n. But if we had 3 letters in our message, right, we might have ZZZ, which would be the number 262,626, and that's bigger than n, right? So this would be too big a block. But as long as we have 2 or fewer letters, whatever the letters are, this integer corresponding to it will be smaller than n. So we use a block size of 2. All right, so let's note that. Which means to code the message happy, first we're going to code HA, and then PP, and then Y with maybe a space at the end. And we're only going to do 1 block. That's going to be plenty enough work to get the idea. All right, so let's code up H and A. So H is the 8th letter of the alphabet, so that's 0, 8. And A is the first letter, so that's 0, 1. So our plain text message is just 801. And it's okay to suppress that first leading 0. All right, so that's what we're starting with. And let's encrypt it. So remember, the trick for encrypting is your ciphertext will be basically your plain text raised to the E modulo n, right? And as the person who's been given the encryption key, you know n is 3737 and E is 23. So if you know the original message and the key, you can find the ciphertext. All right, so let's do that by hand. So we want to calculate 801 raised to the 23, and we want to do that modulo 3737. All right, well, 801 raised to the 23 is, you know, something with 66 digits plus a 6 in the front. Okay, that's a big number, and it's way too big for my calculator to manage accurately as integers. Now I could do this with BC on Unix pretty easily, but let's do it by hand. Okay, just to kind of see that this is actually doable, and it's takes some faith, but it's not as bad as you might fear. All right, so let's use modular exponentiation. So I'm going to observe that 23 is 16 plus 4 plus 2 plus 1. Okay, and if you didn't know that, convert 23 into binary. Right, and that binary representation tells you the powers of 2 that add up to 23. 2 to the 0, 1, 2, and 4. 2 to the 0, 1, 2, and 4. Which means if I can find 801 raised to each of these powers, I can multiply those and find 801 to the 23rd. And I don't have to do 23 calculations. I only have to do 5 to find these powers, and then a final set of calculations to multiply them. So let's do this. 801 to the first is simply 801. And I'm going to write once mod 3737, but this is always going to be the moduli I work on this page. Okay, so 801 is congruent to 801. 801 squared is congruent to, so I'm going to use my calculator, and it's going to be 641601. And that's a small enough number I can do this exactly on a calculator. So I'm going to divide by 3737. And it goes in 171 times with 0.688, etc. left over. Okay, and I'm going to do my trick here. I'm going to subtract 171. To get a number between 0 and 1, I'm going to multiply that by 3737. And I get 2574. All right, 801 to the fourth will be 2574 squared. And so I'm just going to square this. And I'm going to divide by 3737. It's 1772 plus change. I'm going to subtract 1772. I'm going to take that decimal number and multiply by 3737. And this is congruent to 3512. 801 to the 8th. Well, I'm not going to keep writing these down. I'm just going to take 3512, square it, divide by 3737, subtract off the integer part, multiply by 3737, and there's 2044. Got to do one more. So 2044 squared, and I'll divide by 3737. Subtract off the integer part, multiply by 3737, and this is congruent to, looks like I did something wrong. Let me do that again. 2044 times equals, right? And I got my previous results. I don't have to go all the way back to the beginning. Divide by 3737, subtract 1117, and then multiply by 3737. And so I get 3707. Now this should usually come out to be an integer, but because, you know, floating points aren't always exact, you may find a little bit of error at the end, 0.00001 or something 0.9999. But if it's way off, go back and redo that number because you probably did something slightly wrong. All right, so I've got my powers of 2 with 801 raised to each of those powers. So now let's multiply these together. So 801 to the 23rd is going to be 3707 times 801 to the 4th, 3512 times 2574 times 801. All right, and let's do this in pieces. So I'll start off with 3707 times 3512. And I'm going to divide by 3737. And I'm going to stick that in my memory so that I don't make typos again. I'm going to subtract 3483. And I'm going to multiply by my memory. And this is going to be 3013. I'm going to multiply that by 2574. Divide that by my moduli, subtract 2075, multiply by my moduli. This is congruent to 1187 with a little bit of rounding error there. And then if I take that and multiply by 801, divide by my moduli, subtract 254, and multiply one more time by the moduli, I get 1589. All right, that is my encrypted message. That's the ciphertext version of HA integer 801. And so this would be the number that I would put out there and say, hey, here's a secret message. Go ahead and deliver this to Nick, and anybody else who gets this, even though they know that the message was encrypted using this pair of integers, theoretically, they cannot decrypt this. Now, why it's very difficult to decrypt that is, outside the scope of this this talk and this class. But we came up with the decryption key ourselves, right? And we did it because we knew P and Q. And so we were able to find something that satisfied D times E modulo, right? That product. So if you can factor N, you can figure out P and Q, you can find the decryption key. So the first level security on RSA is that given the encryption key, this integer N does not give you P and Q. Okay, it's based on the idea that it's hard to factor this product of primes back into the original primes. And if that's not the case, like it is here, then there's no security to this algorithm. But supposing that these are, several hundred digits each, you get a big product here, it's very hard to go backwards to the original primes. So here's our message, and presumably it's secure. And so let's go ahead and we've received that message, and let's decrypt it. So let's decrypt the message 1589. All right, so RSA, when we worked through the algorithm, we saw the trick to decrypting was basically you just take your ciphertext and raise it to the power D. And you do that modulo N. And your original message should be whatever that is congruent to, mod N. All right, so our ciphertext was 1589. And our decryption key, which was our secret, was 3287. And we want to do this mod 3737. All right, well, how do we do this? Exactly the same way that we did the encryption. We use modular exponentiation. Okay, so the first thing to note is that 3287 is 1100, 1101, 0111, base 2. So we need 2 to the 0, 1, 2, 4, 6, 7, 10, and 11. So we need these powers of, we need 1589 raised to 2 to each of these powers. So raised to the 1st, 2nd, 4th, 8th, not the 8th, 16th, and so on. All right, so we just begin. So 15 to the 1st is 1589. 1589 squared is divided by our moduli, subtract 675, multiply by our moduli, 2,446. So you can skip ahead in the video if you want, but I want to sort of illustrate that even, you know, a calculation like this, which is going to have thousands of digits, is doable in a few minutes with a little bit of knowledge of modular arithmetic and a basic desk calculator. So this thing to the fourth is going to be 3,716. Let's raise that again. So this will be the 8th power. Subtract 3695. Multiply by memory. 441. This is real calc, by the way. No affiliation with them, but I've been using it for years as my only pocket calculator on Android, and it works great. I love it. I should donate to them at some point. Alright, so let's raise this again. So I'll just type in 441 to get rid of my noise over there. So 441 squared divided by 3737, take off the integer part, multiply by the moduli. And you know, if nothing else, you get really good at doing modular calculations on a calculator by doing this. Alright, so 157. My numbers are nice and small for a little while. So that squared is 2227. Well, they're not small anymore. So this number to the 64th, divide by the moduli, subtract the integer. So that's going to be 530. And this you know, works because my numbers happen to be, you know, too big to do strictly by hand, but small enough that they can be calculated exactly in a pocket calculator. Now, if these were 10-digit numbers, this wouldn't be working, right? If they were 7-digit numbers, this probably wouldn't be working, because I only have about, you know, 12 or so digits of precision before we start getting into, you know, floating point representations. But, you know, you would do this numerically. You would do pencil and paper, add and shift, character by character, kind of like what BC does on in Linux. So it's not always, you know, this easy, but for a computer, it's even easier. All right, so let's do that. Squared divided by recall, subtract the 75, multiply by the moduli. So this is 625. All right, there's some more rounding error there, but that's fine. Raise it to the 256. Now I only need to go up to the 2048th power, right? That's the biggest power of 2, less than or equal to 3287. So we're getting there. We got a few more to do. Let's take 625, square it, divide by the moduli, subtract 104, multiply by the moduli. We've got 1977. If we square that and then reduce it, we get 3364. And if I was doing this by hand, you know, at this point I'd change it to a negative number because it would be, you know, about 400, and that would be a smaller number to work with than, you know, 3,000 something. But on a pocket calculator, I'm not worried about it because it can handle this. Divide it by the moduli, subtract 3028, multiply by the moduli. So now we're up to 860. That's a nice number, and now we only have to do one more. This thing raised to the 2048 will be 860 squared, and then reduce that, subtract 197, multiply by the moduli, and we find its number to the 2048 is congruent to 3,411. Alright, and we're done for a moment. Alright, we have to do one more operation to finish decrypting our message. So this final operation will be as follows. 1589 to the 3287 will be 1589 raised to the 2048 plus 1024 plus 2 to the 7th is 128 plus 64 plus 16 plus 4 plus 2 plus 1. Right? And I know this because that's, comes from the binary expression of 3287. So law of exponents, this is congruent to this raised to that. It's also congruent to this raised to the 2048 times this to the 1024 times this to the 128 times this to the 64 and so on. So I'm simply going to read my values from over here and say this is congruent to 3411 times 360, right, or 860, because that's raised to the 1024, times raised to the 128th is 625, times to the 64th is 530, times to the 16th is 157, to the 4th is 3716, squared is 2446, and to the first is 1589. And I got to double check. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I think I'm in good shape here. So all we have to do is this one final multiplication, and that should tell us what our original message was. All right, can we do it? Absolutely. So again, we're going to do that. We're not going to multiply everything out because that would be too large of a number for our calculator to do with full precision. So we're going to do 3411 times 860. And I'm going to reduce this product immediately, modulo 3737, right? And that's not going to change our final answer, but it's going to make our calculations easier. So I'm going to subtract 784, multiply by our moduli, and we get 3652. And I'm going to multiply that by 625. And I've got a number there that I'm going to reduce with our moduli. Subtract 610, multiply by 3737. This will be 2930. And then I'll take that and multiply by 530. And reduce that. So subtract 415, multiply by the moduli. This is 2045. And I'm going to multiply that by 157 and reduce that. All right, so that's 3420. And I'm going to multiply that by 3716. So let me do 3420 times 3716. And I'm going to reduce that. Subtract 3400, multiply by this. And we get 2920. I want to multiply that by 2446. And I get 7 million something. Reduce that, mod 3737. So subtract the 1911. Multiply by your moduli again, and we get 913. And our final answer will be 913 times 1589, which will be 1450757. So that is congruent to our original message, but let's reduce it modulo 3737. So divide by 3737, take off the integer part, multiply back by our moduli. Here comes our original message, 801. So we've decrypted the ciphertext 1589 and turned it back into the plain text message 801. And yeah, there's a bit of work to do there, but I mean, we're doing it by hand, right? This is normally done by a computer. It's not that much work though, right? It's certainly a lot less work than if I tried to multiply 1589 by itself 3,286 times, right? That would be, terrifying an amount of work. So modular exponentiation really, really cuts that down for us. So lots of good number theory going into, you know, the validation that this process will get us back to our original text. But then we also use some of these tricks for modular exponentiation and so on to actually do the calculations inside a computer, or to do them by hand. So anyway, that's a run-through sample of, you know, taking our generating an encryption key, figuring out what the secret decryption key is, and then using that key to encrypt a message, and then using the decryption key to take that and turn it back into the original plain text message. So that's all. I just wanted to kind of work that through once, just because it's one thing to see the theory, it's another thing to actually plug in real numbers and see that it works. So just wanted to run through that. All right, thanks. Bye.